Section 12.7, Atomic Spectra and the Bohr model of the hydrogen atom. If we look at the atomic spectra of hydrogen atoms and measure the wavelengths, we'll be able to calculate the corresponding wave numbers, 1 over lambda. Rydberg found this equation. 1 over lambda is a constant times 1 over m squared minus 1 over n squared. M and n are integers. The Rydberg constant was determined to be roughly 10 million per meter. So that means 10 million waves per meter. The reason behind this Rydberg equation and the Rydberg constant is that the energy of the electron in the hydrogen atom is quantized. Remember, the electron in the hydrogen atom can occupy the 1s orbital, right? It can also occupy 2s, 2p, 3s, 3p, 3d orbitals as well. If an electron is promoted to the 3p orbital, it may jump back to the 2s orbital. From 3p to 2s, there's an energy difference. 3p has higher energy than 2s. So when an electron jumps from 3p to 2s, some energy has to be released in the form of a photon. And it turns out that photon has a red color, and we can calculate the wave number and wavelength of that photon using the Rydberg equation. So now, without proving this, the energy of the electron in the hydrogen atom is -1 over 2n squared atomic unit. N is the principal quantum number. So if you have 1s, 2p, 3d, the quantum number is 1, 2, or 3. Now, what about this atomic unit? One atomic unit is 2,625.5 kilojoule per mole, or 4.35975 times 10 to the power of -18 per electron. So now we can calculate the wavelengths using this information. Let's say we have an electron jumping from level n to level m. M is less than n. You can imagine this n is 3, this m is 2, and then we can calculate the energy of the emitted photon. The energy of a photon is hc over lambda, and that's just the difference between the two different energy levels. This is the energy of level n, this is the energy of level m. We take the difference and we plug in this atomic unit here, divided by 2 because we have 1/2 here. We get a number here. And make sure you cancel the negative signs properly. And then you have 1 over m squared in front of 1 over n squared. And then we get this nice equation. We plug in all the numbers. We have this number here, and we have hc down there. This is the Planck constant. This is the speed of light. Without analyzing the units of these three numbers, I know 1 over lambda has to be in the units of reciprocal meters. So in the end, you just calculate this to get the Rydberg constant right here. This is the origin of the Rydberg equation and the Rydberg constant.